Hello guys, in today's video we're gonna dive into an implementation of variational autoencoders. It's a follow-up video for the variational autoencoders explanation video I made. If you haven't already seen it, I advise you to go and check it out. So I tried my best to make the implementation as simple as I can, and by simple I mean easy to understand. Also, I will link it in the description. I will also link in the description a lab that I really advise you to implement in case you really want to understand variational autoencoders. And basically the lab is the same code, just like it's missing a few lines with a comment of to do, where you have to fill them to make sure that you really understand variational autoencoders and to master the art of implementing them. So without further ado, let's jump right into it. So first we have our imports, very easy. Before you start, go to runtime, change runtime type, and make sure that you have the GPU selected. So here we're just making sure that we're using the GPU. Here we specify the batch size. You can increase it for better accuracy. Now we're using I have two implementations. The first one is like a more simple one. It's on the MNIST dataset, and let me show you a visualization of the MNIST dataset. This is the MNIST dataset. It's a dataset of images of numbers, if you don't already know it. Here we get our train dataset. Yeah, that's it. Now we have to implement our variational autoencoder class. So as I explained in the first video, in a variational autoencoder, first you have an input image, you inject it to your fully connected neural network. So our fully connected neural network had two hidden layers in the explanation video, and then we output a mean vector, a standard deviation vector, and the mean and the standard deviation are used to calculate z in the reparameterization trick, where z is equal to the mean plus standard deviation multiplied by epsilon, where epsilon is first sampled from n01. So we first sample epsilon from n01. Let's say we get 0.6. We multiply it by standard deviation. We add the mean. We get z, the z vector. Then the z vector is so this is fully connected neural network 1. Let me call it FC1. So FC1 is our first fully connected network. Then FC2 would be our second fully connected network. The first one is an encoder, the second one is a decoder. Decoder takes Z and outputs the output image, X bar, and our goal is to make X as close as possible to X bar. Now, I already explained all these in the first implementation. So what should we have as local variables in our implementation? We first need our fully connected layer, FC1. We need the mean vector and the standard deviation vector. Now you can add Z as a variable, however you don't really need it because you're going to calculate Z using the mean and the standard deviation. Then we need our fully connected layer 2 as a local variable, and we need X bar. So that's what I did over here. So in the init function, you will specify your local variables. Now the variational autoencoder inherits from base class nn.module, and basically it's, as I said, as you can see here, it's a base class for all neural network modules. So if you want to make a neural network, you have to inherit from it. We first call our base class initialization function. Then self.fc1 is a linear layer that takes the input size. Our input is of size 28 by 28. I don't know how much that is. I think around 786. I'm not sure. If I'm wrong, correct me in the comments. So here we have 786 numbers, which is the image input, and we output 400. Then so we have just one hidden layer here. In the explanation video, I have two hidden layers. So in my implementation, I have just one hidden layer. Then we take these 400 variables in the hidden layer, and we get the mean and the standard deviation, and the mean and the standard deviation have a z dimension, and here I specified z dimension to have 20, so the mean will have 20 is a vector of size 20, and the standard deviation is a vector of size 20. And then we take the input z and we input it to our decoder network. We get 400 variables, and then in the output we take 400 inputs and we get an image of the same size. So let me draw it over here. So here is our input image of size around 786, which is 28 by 28. Let me just represent 4 in a diagram. So here is our first fully connected layer. Let me draw in a different color. So this is FC1, and I'm just gonna represent 4, but note that they are 400. So every one of the inputs is connected to every one of the nodes of the hidden layer, as shown over here. So yeah, it's you get the idea. And then we have we have to output a mean and a standard deviation. Now I didn't really output the standard deviation, I output the log of the variance. I'm gonna explain why in a second. So here we have a vector of size z dimension, which is 20. This is the mean, and here we have the log variance, also of size 20. So every one of these is connected to everyone in the mean and everyone in the log variance output. And same for the second one. I'm just gonna do like a link. You get the idea. And then we do reparameterization trick. We get z is equal to mean plus epsilon multiplied by the standard deviation. So we have to calculate. We have to use the log variance to calculate the standard deviation first, and then after getting z, which is of size 20. So let me draw z of size 20 in a different color. So here we have z of size 20, and z is and z is of will be inputted to another fully connected layer. So this is fully connected layer 2, and this fully connected layer will have will also have 400 nodes. So you get the idea. I'm not gonna do it. And then this fully connected layer is connected to an output layer of size same as input. So the input had, so let me also draw it in black. So the input had this is x bar, and input had 786 variables, so this will also have 786 variables. So this is a network. X, first fully connected, second fully connected, mean and standard deviation, x bar. Okay, and this is what I did here. FC1, the first fully connected, takes input 28 by 28, outputs 400. The mean, the first output, we have two output layers. So the first output layer takes 400, outputs 20 variables, z dimension for the mean. For the log variance, takes input 400, outputs z dimension. Second fully connected layer, it takes z dimension, outputs 400. That's our decoder network. And the output layer takes 400 and outputs 28 by 28. Now, why did we calculate log variance instead of standard deviation? Well, the answer is really simple. As I said, we're trying, in the first video, we're trying to make the standard deviation between 0 and 1. So standard deviation, we're trying to have it between 0 and 1. And this is what the KL divergence term guarantees. Let's say we get a value, very, very small value, like 0.05. In the gradient update, this will cause a lot of numerical stability, because let's say we update the gradient and we get a negative number. This is really bad. So we got a standard deviation that's negative, that's bad. So you can argue that we can simply just do a ReLo, and the ReLo is the maximum between 0 and x. However, this causes a lot of numerical instabilities. Model really struggles to converge. So the best solution is to, instead of outputting a value between 0 and 1, we output a value between log 0 and log 1. So log 0 is minus infinity and log 1 is 0. So we output the variance between minus infinity and 0. And then we simply get back the standard deviation using the formula that says that it's the exponential of 0.5 multiplied by the log of the variance. Because as you know, the x is equal to exponential log x. Okay. So and here we're calculating the standard deviation. That's why we multiply by 0.5, because standard deviation is the radical of variance. So this is the init function. Now our three functions are encode, reparameterize, and decode. The encode is simply we have an input x. We do our fully connected the encoder hidden layer self.fc1. Then we do a ReLo just to make sure that we get a value, we don't get negative pixel values. We save the output in H, and we have two output layers. So by here we have H. So H is inputted to our two output layers, the mean and the log variance. So to get the mean, we do self.fc mu is mean of H, and self.fc log variance of H. Now for the reparameterization trick, first we calculate the standard deviation. We do exponential 0.5 multiplied by log variance, as I just explained. And then we sample epsilon between 0 and 1. And then we return the mean plus epsilon multiplied by standard deviation. For the decoder, so by here we have z. So we have z by here. We input to the hidden layer fc3, the first hidden layer. There's no second hidden layer, just we have one hidden layer. We input z, okay, to the fc3, and then we do a ReLo just to make sure we don't have negative values. And then for the output layer, we do a sigmoid of the output layer of so we save the value in H. The output layer takes H as input and projects it into 786 dimension. Then we do a sigmoid, and voila, we have our output X. So for the forward, simply we do x equal x dot view minus x is the image. So we do a dot view of minus 128 by 28, and view basically reshapes any function like you want. I prefer it over the reshape function of NumPy. So this one is provided by Torch. You can read its documentation, but basically when you specify you specify the new number of rows and the new number of columns. When you specify -1 in the number of rows, you're basically saying, okay, I don't know how many rows, because your input image may not just be rows by columns. It may be rows by column, batch size by rows by columns. Usually batch size is the first one. So you're saying, I don't know how many rows, because the rows may be just the batch size, and maybe the batch size would be 1. So because we don't know, we just specify -1. Usually we do that. So usually in the view function we provide -1 for the rows, and for the columns we specify 28 by 28. So the whatever input image there is, it will be resized. So here we have our input x. We do mean, and the standard log variance is the self.encode of x. Then z is self.reparameterize mean and log variance. X bar, I called it here reconstruction, is self.decode z. And then to calculate the losses, as I said in the first video, we need the reconstruction x bar the mean, and the log variance. Okay, and so that's it, and then we launch our model. Now for the variational encoder loss, let's go back to what we discussed in the first video. So we have two losses. We have the reconstruction loss, and okay, I don't know why I can draw. So we have the reconstruction loss and we have the KL divergence loss. Okay, let me refresh. Oh yeah, okay. So we have our reconstruction loss is basically the subtraction of all pixel values. For the KL divergence loss, as I explained, the KL is half the mean plus the standard deviation minus log mean minus 1 and multiplied by half. So yeah, that's it. So that's what we do in our implementation. So we do a here we have values of 0 or 1, so that's why we do a binary cross entropy between x and x bar, the reconstruction. So this is basically the first loss, the reconstruction loss. Now for the KL divergence loss, we do you'll ask me why is it minus mean minus log variance dot exponential, which is the standard deviation, by the way, plus log variance plus 1. It's the exact opposite of this one. It's basically because we have minus outside. So as you can see here, we have minus. The formula I just showed has plus 0.5 multiplied. Here we have minus 0.5. So the minus 1 becomes plus 1. The log of variance the minus log of variance becomes plus log of variance. The mean power 2. My runtime got disconnected. The mean power 2 becomes minus mean power 2, and the log and the standard deviation, which is the exponential of the log variance, becomes minus exponential of log variance. And after calculating the reconstruction and the KL divergence, we simply divide them by the batch size. Here we specify the number of epochs. I just did 20 because MNIST dataset is really easy to learn. We iterate our trained data loader. We take every image. We calculate the mean, the standard deviation, and reconstruction. We get the losses. We call loss.backward and optimization.step, and that's it. Here I visualized. So here's input image. Here's reconstruction. So it's of really good quality. And if you wanna generate from scratch, as I said, I did it here in GenGrid, so you can read the code. It's not of the same quality as when generated using the input image. So here in generated, you sample Z from N01 and you see whatever image you get. We get these results over here. And this is for the first implementation, which is a really easy implementation. For the second implementation, it's a bit more complex. So it's on Oxford 3 dataset. So the Oxford 3 dataset is a dataset that contains images of animals. And I just took cats because in my explanation video, I explained using cats. So to do that, in our trained data loader, we have to take a subset. So here we have DS is subset of the dataset. This is the dataset full loaded over here, the Oxford dataset. So to take a subset of it, we specify the types of cat names. You can read the documentation of the Oxford 3 pet dataset, but here I said I want Persian cats, Bengal cats, Bombay cats, and then I got the indices of these names. So I got DS full and I get their indices, and then after I got the indices, I called the subset function, and my data loader was provided the dataset with just like the subset. Okay, and this is how I just got these types of cats. Now, for the losses, it's basically the same loss. For the trained data loader, it's the same, and visualization is the same. What differed in the second implementation is just basically the fully connected layer. So the reparameterization trick is the same, the encoder is the same, the decoder is the same, the forward is the same, just the fully connected layer is different. So if we go back, if we go back to our implementation, we had an input image, fully connected one, mean, standard deviation, Z, fully connected 2, and then X bar. This part, the fully connected one, is different in the second implementation here and here. Basically, because this one is a bit more complicated, because the cat's images are way harder than just numbers, we have to do like what the unit did. So if you aren't familiar with the unit, I advise you to go and watch my video on it. But the unit basically takes an image, applies many convolutions, gets the local features, and then goes up. So here we have our input image, very, very big. We apply many filters, and we get really small images, many small images. So here we have around 1024 images of size 28 by 28. The input was of size 572 by 572, and then we go up. So in encoder of the unit, you first go down by applying many filters, then you do also called convolutions, then you do deconvolution, and you go up. And this is what I did here. So basically, in the second architecture, we have an image of size 64 by 64. We apply filters of size 4 by 4. Okay. And initially, like the first time I have an image of depth 3 and size 64 by 64. So we have an image of depth 3, and we apply 64 filters the first time, all right, of size 4 by 4 with I'm guessing a stride of 2 and padding of 1. Basically, a stride of 2 when you do a conv2d would divide the image by half in size. Okay, basically when you're saying I have a stride of 2, when you pass the filter, you pass it here, you have to jump the filter a full stride. So you, instead of reinitializing it from here, you reinitialize it from here. Okay, so from where you stopped, and this would basically divide the image size by 2. So initially we had an image of size 64 by 64. After the first filter, we'll have an image of size 32 by 32, and this is because we applied a stride of 2. And then we would have an image of size 16 by 16, and then 8 by 8, and then 4 by 4. And initially, the first time we apply convolution, we had the depths of 3. Then we have a depth of 64 because we apply 64 filters. And then we have a depth of 128 because we apply 128 filters. And then a depth of 256 because we apply 256 filters. And then a depth of 512. So we start with 64 by 64 images. We end up with images of size 4 by 4. However, 512. So we have 512 different images. And these images, as I explained in the unit video, contain different local information of the cat, like its ear, like the local features, its eye. So, how about the filter size? The filter, as I explained in the unit video, should match the size of the input. I mean, in the depths should match. So it's always 4 by 4. However, the depth of the filter changes. The first time, the filter should have a depth of 3. So in the first time, we have just the depth of 3. The second time, it stays 4 by 4. Okay. However, the depth should be 64 to match it, and then it should have a depth of 128, then 256, and then 512. I explained that more in details in the unit video. and this is what's done here. So you do a conv, then you normalize the image, and then you do a relu, then again conv, and you jump to depths of 256, normalization relu, then conv, normalization relu, and then you do in the output layer you do a fully connected layer. So the fully connected layer would take 512 inputs multiplied by 4x4, which is the number of pixels, and we would output to Z dimension. Here the Z dimension is 128 because really, I mean, if you can shrink it more, but you need a bigger data set and way more epochs to converge. So that's how we get our mean and our standard deviation. Then in the decoder, just like in the UNet, instead of applying a convolution, you apply a deconvolution, and the deconvolution, instead of shrinking the image with the stride, it doubles the size of the image. So we do conv transpose to D. The first time, before we do our decoder, okay, so we have our mean and standard deviation. So now we get Z. So at this point, we get Z by reparameterization trick. Now we then input Z to a fully connected layer that takes Z dimension as input, which is 128, and outputs 512 by 4x4 to get back because we're doing like UNet. So in UNet we ended up at 512 images of size 4x4. We need to continue from there, but the fully connected layer outputted a Z dimension. So to go back, we do another fully connected layer that gets us to 512 by 4x4. Then for our decoder, we first take a depth of 512, we shrink it to 256. So we apply 256 different filters of depths 512 and size 4x4. And we do a stride of 2 to double the size of the image. So here we would have an image of size 8x8, and then here, so here we would have an 8x8, here we would have a 16x16, here we would have a 32x32, and here we would finish up with 64x64, which is our original size. And at the final one, we do a sigmoid because it's the output layer. And the encoder stays the same, reparameterization the same, decoder the same, forward the same. Just we made our fully connected layer a bit more complex to capture the local features. So we teach the model how to generate a cat. And this is our output. So this is the original image. This is the generated one. It loses a bit of quality, but you're basically generating the image. So this is the cat. This is the cat. This is supposed to be this one. And yeah, that's it. I hope you enjoyed the video, guys. If you did, subscribe would really help me out a lot. If you have any questions, leave them out in the comments. And as I said, I really advise you to do the lab to really get familiar with the topic. See you next time. Bye.